This will be Rudin theorem 4.8. So let x and y be metric spaces and let f be a function from x to y. Then f is continuous, meaning continuous at all points in x, if and only if either of these conditions holds. The preimage of every open set is open. The preimage of every closed set is closed. So these are characterizations of continuity that use nothing but the notions of open and closed sets in the metric spaces x and y. Okay, so let's start by proving that 1 and 2 are equivalent, and then let's prove that 2 and 3 are equivalent. We're not going to go in a cycle because 1 and 2 are sort of, I think, easier to understand together, and then 2 and 3 are easier to understand together rather than trying to go 1 to 2 to 3 to 1. Alright, so let's work on 1 implies 2. Assume you have a continuous function from a metric space x to a metric space y. And let's take any open set in x. So let U subset x be open. So here's the situation. X, y, and here's some open blob U in y. Now, we want to prove that the preimage of U is open in x. The preimage of U is some other blob in x. And the definition of open says to prove that this is open, I need to prove that for every point, let's call it P, in it, there is a ball of some positive radius that's completely inside. So let P be in the preimage of U for the purpose of proving that the preimage of U is open. Now finally I can use continuity. So f of P is somewhere in U. After all, that's what it means to say P is in the preimage of U. And U is open, so that means there's some ball of some positive radius that's fully inside U and that contains f of P. So there's some, let's call it a radius epsilon. So that the ball of radius epsilon centered at f of P is contained in U. Now, f is continuous, and we're going to use the epsilon delta definition of continuity. Given this positive epsilon, since f is continuous at P in particular, there's some, let's call it delta, greater than 0, such that f maps the delta disk centered at P into the epsilon disk centered at f of P. But if everything in the delta disk centered at P gets mapped into the epsilon disk centered at f of P, that means everything in the delta disk centered at P is in the preimage of the epsilon disk centered at f of P. And that's what's needed to prove that the preimage of U is open. Okay, let's prove 2 implies 1. So assume F maps a metric space X to a metric space Y, and the preimage of U is open for all open subsets U of X. And let's reset this picture. So to prove F is continuous on X, I must prove F is continuous at every point of X. So let P be a point in X. So let's say P is here. Then, by definition of continuity, what I need to prove is that for all epsilon, if I look at an epsilon ball centered at F of P, so let's call this the epsilon F of P, that I need that there exists a positive radius delta so that all of the things within delta of P get mapped into that epsilon ball. So let epsilon be greater than 0 for the sake of proving that F is continuous at P. Now, we have proven before that balls are always open. Open balls are always open. So the epsilon ball centered at F of P is an open subset of the metric space Y. That means, according to our assumption, the preimage of this epsilon ball is open. Is open. So let me take the preimage of the epsilon ball. It may not look like a ball anymore. Well, these are arbitrary metric spaces, so we don't know that balls actually look like balls at all, but the preimage of this ball in Y might not look even like whatever the balls in X look like. So let's detect that by making it look like a blob. But it is open, and it contains P, so it at least contains some disk that's fully inside it, some ball that's fully inside it. So let's call this one delta, V delta P. So there's some delta. So actually, what justifies the existence of this delta? It's that P is in this open set. So how do I know that P is in this preimage? To say P is in this preimage is to say F of P is in this epsilon ball. It is because it's the center of that epsilon ball, right? It has distance 0 from F of P. So no matter what epsilon is, certainly P is in this preimage. Then there's some delta greater than 0, such that V delta P is a subset of that preimage. So that means everything in this delta ball is in this preimage. So every point in this delta ball gets mapped by F into this epsilon ball. That's another way of saying F maps the delta ball in X into the epsilon ball in Y. And that establishes that F is continuous at P. Since we did this for all P, F is continuous. Okay, so much for 1 implies 2 and 2 implies 1. Let's verify that 2 and 3 are equivalent. So for 2 implies 3, assume that F maps a metric space X to a metric space Y, and the preimage of an open set is always open. Now, can we prove that the preimage of a closed set is always closed? So let F be a closed set in X. Well, we could use the definition of closed and try to construct an argument using limit points. So maybe, oh, sorry, this should be Y. Let F be a closed set in Y. And we want to show the preimage of capital F is closed in X. So we could try to use the definition, and what we would then try to show is for the preimage of capital F that it contains all of its limit points. In other words, we would want to show that if something is a point in the metric space X and not in here, then it's not a limit point of this set, which would mean that we're trying to find some open disk around it that gets mapped by F to something disjoint from capital F. However, we're going to end up repeating a lot of the work we already did in proving that condition 1 was equivalent to condition 2. And the reason for that repetition is that closed sets are the complements of open sets. So when we work with that limit point definition in this context, it just makes us it naturally makes us want to work with a complement instead, and then we end up repeating ourselves. So let's just work with a complement. It's very direct. Let F be a closed set in Y, then the relative complement Y without F is open. So the preimage of Y without F is open. And the preimage of Y without F is X without the preimage of F. So preimage of complement is complement of preimage. So the preimage operation acts on sets, typically in a way that commutes very nicely with the set algebra operations. Okay, so the complement of the preimage of F is open, thus the preimage of F is closed. And if you want to get 3 implies 2, then you would carry out the same argument, except you would swap the words open and closed. So that's it for the equivalence of 1, 2, and 3. So that gives us a way to use the idea of open and closed sets to characterize continuity for functions from one metric space to another. It's not necessarily giving us a way to talk about continuity of a function at a specific point. It's more talking about global continuity. So condition 1 in the theorem was F is continuous, not just F is continuous at P. Okay, let's look at one kind of trivial example just to highlight a certain misconception that can occur. So let's take, for our x, let's take R2, and for our y, let's also take R2, and let's take the identity function that's certainly continuous, right? And you can see also that the preimage of any open set in R2 is going to be open because the preimage of any set is just itself. It's the identity function. But what if I restrict the domain? So let's say instead of the domain being R2, I make the domain be the closure of the unit disk in R2. So it's still the identity function, just with a smaller domain. Now, let me take an open set in R2, maybe U equals the upper half plane. Let's call it H. Okay, so that can be shown to be an open set in R2. And what's the preimage of the upper half plane under F? It's going to be half of a closed unit disk, not including the boundary on the bottom, but including the arc on the top. Now, this doesn't look like it's an open, nor does it look like it's a closed set in R2. So what gives? We're taking the preimage of an open set, and it doesn't seem to be open. Well, it's not open in R2, but the domain metric space is not R2. The domain metric space is the closed unit disk. So this is the background space that the light set exists in. Not the entire plane, but just the closed unit disk. And this half disk, while it's not open in R2, it is open in the closed unit disk. Now, we've proven before that for a subset of a subspace, like this closed unit disk of a metric space, to be open, it needs to be the intersection of an open subset of the background space with the subspace. So the point is, the preimage of the half plane in this example is not an open subset of R2, but it's the intersection of an open subset of R2 with the domain of this function. So in this kind of trivial example where f is the identity function, it is the intersection of the upper half plane with the closed unit disk, which is the subspace in this example. So that does make it an open subset of the closed unit disk.